In the previous class, we had introduced the Riemann curvature, which is a quantity that measures the curvature of a space-time. Here we have the expression for the Riemann curvature in terms of the Christoffel connection and its derivatives. Looking at this expression, you can see that it has one contravariant index and three covariant indices. We had also obtained a completely covariant form of Riemann Christoffel curvature tensor, which is obtained from the one above by multiplying with appropriate factor of metric tensor. So this can be done in cases where the metric is known. Otherwise, to calculate Riemann curvature tensor, all we need is the Christoffel connection. Well, we had not shown explicitly that this object is a tensor. In order to show that, what we must do is to consider what happens to such a quantity when you go from one frame to another. By doing this exercise, one can indeed show that this is a tensor of one contravariant rank and three covariant rank. However, it could also be shown through other means, especially by considering a commutator of covariant derivatives of some arbitrary vector given by as given here. If you calculate what this covariant derivative gives us, this commutator of covariant derivative gives us, we can see that it results in r rho sigma mu nu v sigma. So this is another way we could obtain the same Riemann tensor, and this form of, or this particular expression that gives Riemann tensor has the advantage that the left hand side of that expression, which is here or here, that is manifestly covariant. That means that quantity has a proper transformation of a tensor, from where you could now deduce that the right hand side also must transform properly like a tensor, and from there argue that this quantity by itself must transform as a tensor of contravariant rank 1 and covariant rank 3. We could now list a few important properties of the Riemann tensor. In fact, we had started doing this in the previous class. Two of those properties can be noticed by observing this expression. One is the fact that under the exchange of the last two indices of the Riemann tensor, the tensor is antisymmetric. You get the component of the tensor with the other reverse order of the last two indices with a negative sign, which tells us that this is antisymmetric in its last two indices. Now, the same holds true for the completely covariant form of the tensor, because coming from here to here, no change occurs, no change happens to the last two indices. So you could write the same even for a completely covariant form of the curvature tensor. The advantage of considering the completely covariant form of curvature tensor is that there are more symmetries that becomes apparent in this form. Especially, you could observe that if you interchange the first two indices, first pair of indices, the tensor is again antisymmetric, meaning R rho sigma nu mu, or R rho sigma nu mu is equal to minus of R sigma rho mu, which makes it clear that the tensor is antisymmetric under the interchange of the last two indices or the first two indices. In the completely covariant form, one more symmetry of the Christoffel tensor component becomes apparent, and that is that if we interchange the first pair of indices with the last pair, giving us R mu nu rho sigma, the tensor is symmetric. So this is the second property, which is also apparent or manifest when you consider the completely covariant form of the Christoffel tensor, Riemann tensor. The last symmetry property is the following, that if we add three Riemann tensor components, all of which are obtained from each other by cyclic permutation of the last three indices alone, then you must get 0. To write it down, if I start with R rho sigma mu nu, I could do a cyclic permutation of the last three indices to bring nu to the second position, sigma to the third position, and mu to the last position. I'll get R rho nu sigma mu, and do one more such cyclic permutation, rho mu nu sigma. The sum of all these three components must be 0. So these are the three symmetry relations, three relations that relate various components of Riemann-Christoffel curvature tensor. One important question that we must answer before making use of Christoffel tensor, Riemann tensor, as well as understanding its physical importance, is how many components this tensor has. Well, at the outset, if you look at such a tensor with a rank 4, it's clear that if each of these indices take 4 values, namely 0, 1, 2, and 3, as we have been using, such a tensor must have 4 Such a tensor must have 4 into 4 into 4 into 4 components. So that comes to 256. So all in all, the total number of components such a tensor would have is 256. However, remember that these are all possible components of the Christoffel tensor. These three relations that we just stated connects many of these components. You can find values of many of these components in terms of the remaining ones by using these identities which connects various components of the Christoffel tensor, Riemann tensor. Hence, we must ask the question, how many independent components such a Riemann tensor has? The way to do this is by making use of these three identities and finding out exactly how many components are independent of the rest. Let us start with the first one. The first identity tells us that if I interchange the last two indices, the position of the last two indices, I get the same Christoffel tensor component but with a minus sign. This necessarily tells us that if I consider the the Riemann component, Riemann tensor component with their last two indices being equal, then that must necessarily be 0. Because as you can easily see, if I have, let's say, R rho sigma, let us keep rho, the first two indices, fixed for now and put some value for mu and nu which are equal. Let's choose 2. R rho sigma 2. This identity or this equality tells us that that must be the same as minus of R rho sigma 2. Now such a thing can happen. A number being equal to the negative of itself could happen only if that number is 0. That means all such components where the last two indices are equal should be 0. That makes the counting much easier now. We know that we should only look for those components in which the last two indices are different. That too, even when they are different, if I know R rho sigma mu nu, it is easy for me to find R rho sigma nu mu because it is the negative of the other. Hence, it is good enough for me to find how many possible components there are where mu is less than nu. The other case where mu is greater than nu can be found if you know what this particular component is. And that's easy to count. After all, mu being less than nu, a value of mu and that is less than nu can be chosen out of these 4 possible values allowed for mu and nu, and that can be done in 4 choose 2 ways. It is a matter of taking 2 numbers out of these 4, and the number of possible ways I can do that is 4c2, whose value, as we know, is 6. So by making use of the antisymmetry of the last two indices, we learn that the the Riemann Christoffel tensor components that are independent are for fixed values of our first two indices, rho and sigma, are only 6 in number. And let's move to the second equality in this. The second equality tells us that if I interchange the first two indices alone, then again I get Now I don't have to repeat whatever I said for the last two indices. It's clear that there is an antisymmetry in the first two indices, which is very similar to the antisymmetry in the last two indices. And hence, for fixed values of the last two indices, mu and nu, the number of distinct components which are independent, again, must be 4C2 equal to 6. Okay, so we know that in this tensor written as, let's write it here, R rho sigma mu nu, the possible number of independent components for different values of mu and nu are 6 in number, and those 6 can be represented by if those 6 can be represented by a new index, let's choose it to be k, then that k can take values running from 1, 2, 3, etc. 6. Similarly, since the same antisymmetry is true, holds true for the first two indices also, if I represent the number of independent combinations for which rho and sigma are different with an index j, that j will also run over the same set of values 1, 2, 3, etc. 6. Now it's clear what possible combinations we are talking about. Just to understand, make it more clear, I'm talking about the combinations of values mu nu equal to, let's say, 0, 1, 0, 2, 0, 3, then 1, 2, 1, 3, and last 2, 2, 3. So these 6 values that the index k takes represent the following. K equal to 1 represent 0, 1, k equal to 2 represents 0, 2, etc. K equal to 6 represents the last combination 2, 3. A similar thing can be done for the pair of indices rho sigma also. Now you can see that we could also have written the same as R, J, K, where J and K run over 1 to 6. This way of writing it makes it obvious how many independent components this tensor now has after taking into account the antisymmetry of the first two indices and the last two indices. That is given by number of possible values of j into the number of possible values of k, which is 6 into 6 equal to 36. So we started with a tensor having 256 components, and now have concluded at this point that not more than 36 components of it can be independent of each other. Well, so far we have only made use of the antisymmetry property of the Riemann tensor. There is still the symmetry property of the Riemann tensor that needs to be taken into account. Now it is easy to take this symmetry property into account if we follow this particular notation, this way of writing the Christoffel tensor. This symmetry property can be written in terms of these indices as the interchange of these two indices giving us the same tensor component as before, as the one before the interchange. Which means that in these two indices, this looks like a symmetric tensor. The question is, how many such components we can have? Well, since j and k can take 6 different values, the question is now, how many independent components a 6 cross 6 matrix can have? This is so because when I write rjk, it's clear that since each of them take values from 1 to 6, this actually represents the jth row kth column component of a 6 cross 6 matrix. And this identity tells us that that 6 cross 6 matrix is a symmetric matrix. How many components can how many independent components can a symmetric 6 cross 6 matrix have? That is given by 6 into 6 plus 1 divided by 2, which is 21. Thus, we have arrived at this number 21, which is the number of the maximum possible independent components of the Riemann tensor. Okay, so far we have made use of the first two of the three identities, algebraic identities, that Riemann tensor has to satisfy. There is the last property that is still remaining that we must make use of. We should see whether the last property puts any more restrictions on the total number of independent Riemann tensor components. To make use of the last property, we should first note or check whether this property gives us anything different than what was given by the previous two identities. To do this, let us consider different possible components or different types of possible components of the Riemann tensor. For instance, let's start with a Riemann tensor component with all their indices being equal. For instance, R, if I choose rho equal to sigma equal to mu equal to nu equal to 1, I get the component R1111. For such a component, let us ask whether this identity gives us anything that is different from what would be given by the previous identities. Well, if you look at this type of a tensor component, it's clear that its first two indices are the same and the last two indices are the same, which tells us, as per the antisymmetry property that we just discussed, such a component must be 0. If such a component is 0, then it's clear that this identity is not going to give us anything new than what was given by the antisymmetry property already. So there is no need to consider this type of a component. Next, let us consider the component in which any three of these indices are equal. We can choose them to be any arbitrary 3 out of the 4. I'll just show you one example in which I choose rho equal to sigma equal to nu equal to, let's say, 3. If I consider this type of a component, then we get R, since rho is 3, sigma is 3, mu is not fixed, and nu is also 3. This is the component. This is one example of a component in which this holds true. Now it's clear that if you look at this component, its first two indices are the same, and hence it must be 0. Now if you write the next component also, next two components also, you see that the same holds true. In fact, in the very next component, the same thing happens, that the first two indices are the same, but in the last one, you have the last two indices being the same. In any case, we see that for such a Riemann tensor component in which 3 of its indices are the same, if we write this identity, you have terms in it, all of which are 0 already according to the first antisymmetry property that we discussed. So this identity does not give us anything new even for this type of a component in which 3 indices are the same. So we should consider nothing more than a tensor component in which at most 2 indices are the same. I'll show you this only for one example. You can do the check for the remaining choices of indices. Let me choose rho, the index rho. In fact, let me choose the index sigma and mu to be the same and take its value to be, let us say, 2. The tensor component that we get with sigma equal to mu equal to 2, if for that tensor component, if I write this identity, the first term in it will be r, rho, sigma is 2, mu is 2, and nu is allowed to be anything. The next term in this is r, rho, nu, sigma is 2, mu is 2. However, we know that this term is of 0 as per the antisymmetry property of the last 2 indices. So let me set that to 0 already. And the last term is r, rho, mu is 2, nu is whatever, and sigma is 2. And all of them must add up to 0. Since the second component is already 0, I could now write the resulting equation as r, rho, 2 nu equal to minus of r, rho, 2 nu 2. Looking at this identity, it is clear that this identity could also have come from the antisymmetry of the last 2 indices, and hence it's nothing new that the last identity has given us. So this now tells us, in fact, you can repeat the same exercise for any choices of the 4 indices, which are any 2 choices of 4 indices being equal, and you would get a similar result. Which now tells us that we need to consider only the Riemann-Christoffel tensor component in which all the indices, all the 4 indices are different. And such a component, if I start with the choice of rho equal to 0, sigma equal to 1, mu equal to 2, and nu equal to 3, this is the component that we have. And for this component, the identity has the form r 0, 3, 1, 2 plus r 0, 2, 3, 1, all added giving us 0. Now, how many components does a Riemann tensor have such that its indices are different? That is given by the permutations of the 4 numbers 0, 1, 2, 3. The total number of permutations of 4 numbers is 4 factorial, which is equal to 24. For 24 components, we could write similar identities. However, you can easily check without much difficulty that the identity written for the remaining components with indices being different can be obtained from this one by either doing the interchange of the first 2 indices, or doing the interchange of the last 2 indices, or by means of interchanging the first pair of indices with the last pair of indices. Thus, those identities are not going to be different from this and what this identity together with the symmetry and antisymmetry properties could give us. So in practice, we don't have to consider all those identities. Thus we can say that there is only one more condition or connection between Riemann curvature tensors that we could write down, and that is given by this one condition. This clearly enables us to write one of these three components in terms of the remaining two. So that one component is no longer counted as independent. We must subtract that one more component out of the number 21 that we have obtained. Thus, the total number of independent components is 21 minus 1 equal to 20. So a Riemann-Christoffel curvature tensor has 20 independent components.